In section 2.3, we studied prime numbers, and you learned that every natural number greater than 1 that isn't a prime itself can be written as a product of primes. And you got quite a bit of practice in doing that. For example, if you were going to prime factor the number 84, let's see, that would be 2 times 42, which is 2 times 21, which is 3 times 7, or 2 squared times 3 times 7. So we already know that, but I'd like to add something that wasn't in section 2.3 because we don't have the background to prove this theorem. And that is that each number that's not a prime itself can be prime factored in one and only one way. There's no other way to write 84 as a product of primes. We could change the order. We could write it as 2 times 7 times 3 times 2. That's a prime factorization of 84, but they're exactly the same primes. 2 factors of 2, 2 squared, 1 factor of 7, 1 factor of 3. So this prime factorization is, we say, unique. Now notice we could also write this as 14 times 6, right? 2 times 7 is 14, 3 times 2 is 6. So this is a factorization of 84, but it's not a prime factorization. There's one and only one prime factorization of each natural number greater than 1 that isn't a prime itself. Keep in mind that this uniqueness of prime factorization is a very important theorem, and we are going to just accept it as being fact without proof. Now the other thing I'd like to look at in this short video is the prime factorizations of perfect squares. Now what is a perfect square? Well, it's a number like 9 because 9 is equal to 3 squared. Or it's a number like 100 because 100 is 10 squared. So you can easily see what a perfect square is. And what I want you to notice is something that always occurs in the prime factorization of a perfect square. So let's look at some of those. Let's see if I can scroll down a bit here. Let's take one example. Let's take 40 squared. Let's take 40 squared. 40 squared is 1600, and it's 40 times 40, and 40, you can go over on scratch paper, you'll see that's 8 times 5, or 2 cubed is 8 times 5 times 8 times 5. So we have now prime factored 1600, but let's put our 3 factors of 2 together with these 3 factors. We have 6 factors of 2, 2 to the 6th, and we have 5 times 5, or 2 factors of 5 is 5 squared. So there is 40 squared. Let's look at 12 squared. That's 144. Again, let's write it as 12 times 12. And then 12 is 3 times 4, or 2 squared times 3. And the other 12, 2 squared times 3. Gathering together our factors of 2, we have 4 of them, and 3 factors of 2. Well, let's look at one more perfect square. Let's look at a bigger one. Let's look at the number 108 squared. On my calculator, I got 11,664. So that's 108 times 108. And if you just go over on some scratch paper and factor 108, you'll get 2 squared times 3 cubed. That's 108. And we're putting it in twice. Notice what happens is each time we've done this, we have doubled the exponent on the number the exponent of the primes in the prime factorization of the number that we are squaring. So instead of having 2 factors of 2, we now have 4 factors of 2. Instead of having 3 factors of 3, we now have 6 factors of 3. So let's look at the exponents on these prime factors of a perfect square. 6, 2, 12 squared, 2 to the 4th, 3 squared, 108 squared, 2 to the 4th, 3 to the 6th. Each one of those exponents, 6, 2, 4, those came from doubling the exponent on the number that in the prime factorization of the number that you were squaring. So if each one of those numbers is a positive integer doubled, then what kind of number are the exponents on the primes of a perfect square? Well, they all come from doubling, so they are all even. These exponents on the primes in a perfect square are all even numbers. So let's write this result down, and you need to remember this for a proof that we're going to do later in section 2.7. So the result that we just observed, let's write as a fact. Each prime in the prime factorization of a perfect square occurs an even number of times. Or we could say all exponents are even numbers. When you prime factor a perfect square, all the exponents on the primes will be even numbers. And don't forget the first theorem that we introduced, that a prime factorization of any number is unique. There is no other way to do it.